Hey guys, what's going on? This is just a quick video that I made for some friends in understanding the master method. I'm going to cover it in three different ways. I'm going to start with the high-level concept of what we're trying to do. I'm going to give the simplified version, kind of an easy to understand way of how to perform the actual master method, and then the mathematically precise way, which is going to be the way that you're going to want to explain it if you're taking any sort of computer science or algorithms classes. So the high-level concept of the master method is that we need to take a quick view of asymptotic notation. So asymptotic notation says if we have an algorithm that runs at, say, n squared plus 3n plus 9 runtime, where n is the size of the input, we want to be able to kind of simplify the form of this and see for a sufficiently large n, what is the actual runtime of the algorithm. And for asymptotic notation, we usually call that big O as the worst case. And we say the big O is n squared because the worst case, the one that we want to follow, is n squared. And at a sufficiently large n, we're going to notice a negligible difference between, say, the 3n and the plus 9. So a good example would be if we needed to find a number in an array of random numbers, what we can do is use the quicksort algorithm, which runs at nlogn, and that'll sort all the numbers. And then we can just search, do a binary search, which runs at big O log n time. So our function, our algorithm, is essentially big O n log n plus big O log n. And at the end of the day, that becomes big O n log n, since that is the value that increases the most with a sufficiently large n. Now, the high-level idea of the master method, we must have our formula in this form where we have t of n equals a times t to the n divided by b plus f of n, where a has to be greater than 0, b needs to be greater than 1, and f of n can be greater than or equal to 1. So, for example, 2t n over 2 plus n, or 9t n over 3 plus n. And we can identify our a's and our b's and our f of n functions. There's three cases for the master method. If the reoccurrence relation, which is n log base b to the a, if that's greater than the f of n function, which means that our recurrence of t to the n winds up being greater than our f of n, then that's case 1. If they're equal, that's case 2. And if the recurrence relation is less than the function, then that would be case 3. There's a little special provision in case 3, but I'm not going to cover that right now. I'll get that once we get to the mathematically precise area, and I'll show some examples. So in this first example, we have 2t n divided by 2 plus n. We identify our a as being 2, we have b as 2, and our f of n is n. So if we look at the recurrence relation and we say, okay, that is n to the log base b of a, we know the values for a and b, so we just plug those in, where it's log 2 divided by 2, or sorry, it is log n base, it is n log 2 to the 2, and that winds up becoming, that log formula becomes 1, so we have n, and that's the size of our recurrence relation, which is the same as our f of n, where n equals n. So this is a case 2 situation, and what we are left with is t of n is big theta n to the log base 2 to the 2 times log n, which comes to n log n. Our second example, we have 9t n divided by 3 plus n. We identify our a's, our b's, and our f of n, and we have n to the log base b of a, plug in our values, and that log formula winds up becoming the answer 2, which gives us n squared as the value for our recurrence relation. Now we notice that n squared is larger than n, which gives us case 1, which means that our recurrence relationship is at n squared. And so for our asymptotic notation, we have theta n squared. For mathematical precision, we look at the cases again. The idea is the same, where we have our recurrence relation n log base b, or n to the log base b a, if that's greater than our f of n function. But to be mathematically precise, we need to say if f of n is equal to big O of n to the log base b a minus some epsilon, then t of n is theta n log base b of a for an epsilon that is greater than 0. What that means is that we're looking for f of n that has to be better, as in it has a shorter runtime or a lesser runtime than the recurrence relationship. This is just a kind of a wacky way of writing the recurrence relationship needs to be bigger than f of n. For case 2, we do something a little similar, where f of n equals theta, or if f of n equals theta n to the log base b of a, then t of n is theta n to the log base b of a times log n, which is very similar to what we had earlier. Case 3 gets a little interesting, where similar to case 1, we have this n to the log base b of a plus some epsilon as opposed to some minus. And when you are using the big omega, which is the best case. So in case 1, we have, is it better than the worst case? In this one, is it worse than the best case? Then t of n is theta f of n, since that is the higher growing asymptotic value, for n epsilon greater than 0. If f of n satisfies the regulatory condition, which basically comes down to this needs to hold for large enough values. I'm not going to spend a lot of time really explaining this. Just know that for case 3, this is an extra stipulation that you need to account for. And because of this condition, the master method cannot solve for every recurrence for the given form. So let's take a look at our example 2 again, where we had 9t n divided by 3 plus n. We pull out the a, b, and the f of n. We replace the n to the log base b of a to the actual values. We receive n squared. N squared is larger than f of n. And here's the mathematically precise way that we can express this, is because f of n equals big O of n squared minus some epsilon, we can identify this epsilon as 1, and that 1 is greater than 0. Therefore, t of n is theta n squared. Slight variation, very similar to what we did in the earlier example. Let's take a look at case 3. So we have t of n equals 3t n divided by 4 plus n log n. We pull out a, b, and f of n. We look at n to the log base b of a. We replace that with 4 to the 3. Without doing the actual math and figuring out what this logarithm is, we know that log base 4, 3 is less than 1. Therefore, we have n to some value less than 1, which makes it less than n itself. And because n, or less than n, is less than n log n, this gives us case 3, where the recurrence relationship is growing at a slower rate than the initial f of n function. And because of this, we can write f of n equals big omega n to the log base 4, 3 plus some epsilon. Sorry, that was supposed to be an epsilon, not an n. Now we need to take a look at the regulatory condition. The following should be true. A times f of n divided by b must be less than or equal to f of n times some c that is less than 1. So we rewrite our formula. We know that f of n is n log n. So we have a times n log n. And our n's are n divided by b, which is less than or equal to c times f of n. We can translate this, fill in the answers. So we have our a as 3, our b as 4. So we fill that in. And then we can do some math to simplify this. And we see that we have essentially 3/4 times n log n, which is less than or equal to n log n times some c. And what that'll give us is that if we use the c value 3/4, which is less than 1, we can make a formula that is greater than or equal to this 3/4 n times log n over 4. Therefore, since the regulatory condition holds, we have theta n log n. Here's our last example. This is going to be a little bit trickier. We have t to the n, tn equals t 2n divided by 3 plus 1. Now remember, we need to rewrite this in the form of a times t n over b plus some f of n. So if we rewrite this with 1 times t of n divided by 3 halves plus 1, we have our a as 1, our b as 3 halves, not 3, and then our f of n equals 1. Or if we wanted to put it in terms of n, it would be n to the 0. So we go back to looking at the n to the log base b of a equals n to the log base 3 halves, or 1.5, to the 1, which equals, for any log, no matter what base, if it's a log of 1, that comes out to 0. So we have n to the 0, which is 1. As 1 equals our f of n, which is also 1, or in terms of n to the 0 is also n to the 0. This is a case 2 relationship, which gives us t of n equals theta n to the 0 log n. N to the 0 is 1, so we can simplify this to just theta log of n. And that's all there is to it. Hopefully this will help you out, and if you would like more videos on computer science related topics, please leave a like and a comment down below.